the purpose of experiment 3 is to indirectly determine the resonance energy for benzene using combustion data and the Hess's law. Okay, so let's look at these two molecules. So they are both the representation of a benzene molecule, right? The difference is for this one, I show there are 3 carbon-carbon double bonds. And for this one, I show that essentially there's no difference between the single bonds and the double bonds, right? So this shows that all 3 carbon-carbon double bonds are conjugated. That's the real molecule that's actually is in benzene, right? Because we cannot distinguish the double bonds with the single bonds. As a matter of fact, that 3 conjugated double bond structure make benzene more stable than 3 single bonds. The stability we gained from conjugated double bonds, the energy we got is called the resonance energy. And how can we measure the energy, since we say that's the energy level that's lower and caused by the conjugated double bonds? Essentially, there's no way to measure that conjugated contribution individually. There is no direct measurement of that energy. The method, however, we can use is to use the Hess's law. So remember in the homework 1, question 1, we use the Hess's law to measure the unknown, the hypothetical reactions delta H, using the delta H from the known reactions, right? In this case, we can do that as well. In order to calculate the resonance energy, then we need to figure out what kind of a reaction we should use, or is there any hypothetical reaction we should use to figure out the energy lowered by the conjugated carbon-carbon double bonds. So let's consider this hypothetical reaction. If I have this molecule that have 3 isolated carbon-carbon double bonds. So you'll notice these double bonds are separated by 2 carbons, so they are not conjugated, right? And there are 3 of them. And look at how many carbons out there. It's 12 carbons and 8 hydrogen. So this molecule is called 1,5,9. So no matter which one you start with, you will find 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll find that there are 3 double bonds at the location of a 1,5,9. So this is a 1,5,9 trans-cis cyclododecahedron. Okay, we call this molecule TTCC, and the TTCC has 12 carbon atoms and 18 hydrogen atoms. And if you count a number of bonds, there'll be 9 carbon-carbon single bonds and 3 carbon-carbon double bonds and 18 carbon-hydrogen single bonds, right? So this can become a benzene molecule, which has 6 carbon, 6 hydrogen, and the cyclohexane molecule. And the difference in benzene molecule is that right now, this carbon double bonds are conjugated. And in this case, the carbon-carbon double bonds are not conjugated, okay? And if we will look at the amount of chemical bonds on the right of the equation, still 9 carbon-carbon single bonds and 3 carbon-carbon double bonds and 18 carbon-hydrogen single bonds. So that's exactly the same as before. So same amount of atoms, same amount of chemical bonds. If there is such a reaction, the delta H for this reaction will be the energy change from single double bonds to conjugated double bonds. right? The only thing that's changed in this reaction is 3 completely single isolated carbon double bonds becomes 3 conjugated carbon double bonds. So we can possibly use this equation to calculate the delta H and then figure out the resonance energy of benzene, right? Does that reaction exist? The answer is no, that reaction does not exist. So we need to use some indirect measure to figure out the delta H of that reaction. One way to do that is if we can use oxygen and have a TTCC burn in oxygen and have benzene burned in oxygen and have cyclohexane burn in oxygen. Will they have the same product or the same final state? So let's look at that. So TTCC will cost this much of oxygen, and then eventually it becomes 12 carbon dioxide plus 9 water and heat. And for this one, it's the same. So if we supply enough oxygen, the final product for benzene combustion will be carbon dioxide and water. And the final product for cyclohexane combustion will be carbon dioxide and water as well. So in the end, they will have the same product. However, the energy difference we're going to look at will be the resonance energy. So we can use Hess's law to calculate the delta H for this hypothetical reaction. Okay, so these you can refer to the handout. I'll point you where the handout is in equation 3 to 13. Okay, so in this experiment, it looks pretty straightforward. We're going to do 3 combustions, and after we combust them, we can measure how much heat we get from each reaction, and then we use the Hess's law to determine the resonance energy. The exception here is the benzene. Remember in homework 2, I asked you guys to look for the delta H combustion value for benzene, because benzene molecule is a carcinogenic. So we don't want to use that in class. So in the video, you won't see we combust benzene molecules. So in the data set, you will have combustion data for TTCC and the cyclohexane, and you will use the literature value you find in homework 2 for benzene. Once you measure the heat of a combustion of TTCC and the cyclohexane, you will use the equation 3-1 and 3-2 to calculate the delta H of the reaction. So those are the equations in the handout.